Okay, and the first is the introduction. Droughts are typically divided into metallurgical, agriculture, hydrological, and socioeconomic droughts, and there are close relationships between the different types of drought. And this translation between different types of drought is referred to as drought propagation. These days, there are many researchers focusing on the propagation from metallurgical to agriculture and hydrological drought. It has been found that the propagation of drought in hydrological systems have the characteristic of the aggregation, attenuation, lag, and prolongation. The various studies quantify the correlation and propagation characteristics between the different types of droughts. Also, correlation coefficients and cross-wavelet transforms were used to reveal the relationship between the different types of droughts. However, the previous studies have not yet clarified the drought propagation relationship since the development of high metallurgical to other type of drought is rather complicated. Therefore, this study aimed to construct the drought propagation model by using the Bayesian networks and coupler function and to quantify the propagation probabilities between meteorological drought and hydrological drought. The meteorological drought becomes the lack of precipitation, and the prolonged deficiency leads to the development of agriculture and hydrological drought. And this change of the drought type is called drought propagation. The concept of drought propagation was introduced by these studies, and recently Van Loon defined the drought propagation as the transition from meteorological condition to hydrological drought. The propagation of drought through precipitation to groundwater water is illustrated in here. Here, the hydrological drought of year 1 is related with the severe precipitation deficit. The Bayesian network model is the probabilistic model that can describe the conditional dependencies of set of random variables. And the network consists of a set of nodes, like here, and arcs. And this direction of the arc is represented relying on the cost relationship among the nodes. And the relationship between the nodes is defined as a conditional probability which is based on prior information or statistically observed correlation. And the conditional probability is calculated based on Bayesian theorem, like here, and which describes the probability of an event based on conditions that might be related with the event. The probability of hydrological drought given by each class of meteorological drought, the concept of conditional probability was calculated using the Bayesian network model. The joint distribution of fxy based on the coupler function is independent variables being uniformly distributed on the interval 0 to 1 is formulated as follows. The coupler functions can flexibly connect two or more variables having different kind of marginal compared to other bivariate distribution models. Here in the Campbell, normal, ZV, and logistic expressions are fitted to the drought series to determine the margin distribution. And the five commonly used couplers from the Archimedean families are considered, which is consist of this. And the Clayton Campbell Frank coupler model is in here. Now this is the study area and the data. We use the Han River. The Han River is the largest river basin of South Korea here. And this study conducted the series of basins of Han River Basin. The daily precipitation and runoff data of 1967 to 2013 was applied. The precipitation data collected by the KMA were area averaged by T-sense polygon method and converted into subbase scale, and the runoff data for each subbasin were widely adopted by tank model. And this is the framework of our study. The main goal of our study is here to estimate the propagation probability, which is defined by this conditional probability of BM model. The first step is the marginal distribution of joint probability was defined by the precipitation and runoff data. And the joint drop probability was represented by this Koplar function, and use these both distributions. The conditional probability of the probability of SRI conditional on SPI is able to estimate. In this case of study, the SPI was classified into 3 stages, and finally we can estimate the propagation probability of each meteorological drought station using this equation. The meteorological and hydrological drought were estimated by using SPI and SRI at least respectively on weekly time scale. The daily data were aggregated into weekly time scale, and the marginal distribution was up. And the marginal distribution were transformed into the standard number distribution. After identifying drought events from the time series of SPI and SRI based on the run theory, drought states were classified into this table. We can express the propagation probability using the BM model like this figure. And the propagation probabilities are estimated by using the conditional probabilities using this equation. In this current study, a coupler is utilized to construct the joint distribution of BN. The coupler method has been proved to efficient in connecting the marginal distribution to joint distribution for vibrate random variables. The conditional probabilities of SRI under different drought conditions of SPI can be formulated as follows. Firstly, now is the result. Firstly, we examine the joint distribution of the propagation probability. The joint distribution is modeled based on the weekly SPI and SRI series using Koplar-based method. The Gamber and normal and GV logistic distribution were applied, and the normal distribution were determined to the best fit for SPI and SR. And the 35 Archimedean couplers were used to, and low likelihood was calculated to choose the best fitted marginal distribution in each subbasin. The joint distribution of SPI and SRI were structured like here. The conditional probabilities Occurrence of hydrological drought under the moderate, severe, and extreme condition of meteorological drought were estimated using these equations. The figure was this figure is the propagation probability under moderate and severe and extreme SPI. The propagation occurred mostly when the meteorological drought was extreme drought. And this red text in sub-basin has the higher probabilities than other basins. Here we estimate the propagation probability based on SPI interval. The propagation probability was increased with the increase of drought level. It means that when meteorological drought becomes serious, the drought is able to trigger higher probabilities of hydrological drought. Now, the seasonal propagation probabilities were also calculated, especially the probabilities in the spring, summer, autumn, and winter range from here is respectively. The propagation probability was higher in summer here, and the lowest is in winter season here. It means the high hydrological drought was easily triggered by meteorological drought in summer season. During the June to August, the higher temperature caused higher evaporation from stream flow, and stream flow was low level until the start of the monsoon. It makes the highest probability in summer season. Now is the conclusion. This study estimates the drought propagation probability using Bn and Kepler function, and the drought propagation probabilities of different states of meteorological drought into different states of into the hydrological drought. The Bayesian network-based drought propagation model is easy to construction, and its structure is based on cause-effect relation between the variables. And joint distribution of Bn can be represented by the Kepler function. The special pattern of propagation probabilities reveal that some areas which show the relatively high probabilities need to properly mitigate the hydrological drought. In addition, the sensitivity of hydrological drought responding to different meteorological drought conditions is another unsolved question in drought propagation, which is helping in decision-making stage for drought risk management. Further studies are needed to quantify the effect of human activities, climate controls, and catchment characteristics on hydrological drought and propagation. And this is end of my presentation.
Okay, thank you very much, Chie-Shin, for the interesting presentation. Is there any question for Chie-Shin? Okay, so I have one. So can you explain a bit more about the study area of your research? What is the study area?
Oh, sorry. Okay, my study area is the Han River subbasin. I can show the figure in here. Here is my study area.
Okay. So the study period is like 50 years of precipitation data, right?
Yes.
Okay. Okay. Thank you very much for your presentation.
Okay, thank
And
you.
yeah, and we moved to the second speaker. The next speaker is Sumiyat Uranchimek and Yonhan Kwon from Sejong University with the presentation of development of non-stationary frequency analysis of rainfall based on VMN QR method. So are you here? I can't hear you. So please turn on your speaker.
Hear me now? Hello? Hello?
Hello. Maybe increase the volume of your mic, please. It's we can't hear you clearly.
Maybe it's because of the internet speed in here. Actually, I'm coming up here in convention center, but I'm the one who is in the room. So
Is
yeah.
how about other participant? Can you hear Sumiya well? So if you think you are ready, you can start your presentation.
Okay. Is it showing? Okay. Good morning, everyone. My name is Somya, and I'm postdoc at Sejong University. Today, I'm going to present about the non-stationary frequency analysis method based on BMN QR method, which will be explained in the later. The content will be introduction, methods and data, and results and conclusion. So first of all, the introduction. The precipitation changes in which the climate change can differ, especially and temporarily for regions due to their geographical locations, especially if some of the extreme events such as floods and droughts have been the main case of the natural disasters in many parts of the world. The hydrological circulation is likely to be accelerated with the increase of water vapor in the under the climate change, or in other words, it's global warming. So such that extreme rainfall events are more likely to occur more frequently. It's even reported in the IPCC IPCC documents that frequent extreme rainfall events have been observed in many regions over the world. So overall, the societal infrastructures will be the more vulnerable to the extreme rainfall condition in the changing climate. The such conditions bring some problems, especially in non-stationarity in the precipitation extreme has been the major concerns of such natural weather change. So the change in the rainfall distribution affects the current operations and future design criteria for the water resource system. Uh, the change in the rainfalls have been assessed by the main candle and KPSS and ADF tests or the long time of periods. However, these methods have some limitations and they have sensitive to the outlier and serial correlations. And moreover, the traditional approach for the trend analysis is not appropriate for the extremes since it's mostly focused on the mean or median of the time series. So in this study, I try to address such problems and develop a model that can address trend analysis and at the same time can perform a can do a frequency analysis. So quantile regression is the model that can better identify the distincts of the changes in the time series data, not only the median one, just the any given percentiles. So quantile regression models allows flexibility to the estimated conditional mean or any quantiles of the response variables. So, however, the quantile regression has some downsides, which is cannot systematically estimate the parameter uncertainty and the other excuse me. 보이나요? And we are trying to address some downside of the quantile regression models and also implementing quantile regression model in Bayesian approach to better explore the distributional changes and assess the uncertainties. And this is the regular Bayesian quantile regression model, which can produce any quantile lines or the time series. And however, these quantiles estimated by separately, and there is no assessment on the uncertainties of these quantiles. And if the consequence of the separately estimated quantiles can make a problem that quantiles crosses, like showing in the in this picture. So in this study, we try to address these three problems. Each quantiles are estimated separately, and no assessment on the uncertainties can be improved by implementing quantile regression model into the Bayesian inference. And this quantile crossing problem can be improved by the implementation of non-crossing constraint in the model. So Bayesian inference requires a likelihood, but quantile regression model has no distribution to the model. So in this case, the many studies suggested that asymmetric Laplace distribution for the error theorem and making the error theorem minimizing the error theorem is the one of the method to implement quantile regression in the Bayesian inference. So we implement the ARD to the error theorem, and the ART is explained as this as in the showing in this slide, and this error term can be rewritten as the linear combination of two random variables. And if we rewrite the regular quantile regression equation, we can get this red one, which is explained by the linear theorem of the error, linear explanation of the error theorem. And after that, we implemented this in the Bayesian format, so we can model as it is shown in the red box, and the all model is developed in the Winbox programming, which is MCMC sampling program. And the model can improve. Model improves this. Excuse me. And the model we developed in these studies can address these questions. If you see this quantiles, it can give you the uncertainties at the first, and then left side figure shows some crossing problems, and which is still improved in the right side figure, which is after the non-crossing constraint is implemented, so the model can fix these downsides of the quantile regression model. And for the comparison purpose, we have done some well-known methods of trend analysis and also the frequency analysis, which is the design rainfall estimated by the GEV distribution, which is mostly used in South Korea. The model data is obtained from the Korea Meteorological Administration, and where 93 weather observation, 93 weather observation, which has the long period of recording. So we use this, and before we implement our method, we performed some quality assessment on these models. Excuse me. And we have selected 50 out of 93 stations in these studies based on the continuous observation and less than 5% of missing values during this selected period, 73 to 2015. And the results, if you implement the developed model, we can get each quantiles with their uncertainties. If you look at the start of this time series, there is some blue line. If you get this each quantile lines from this blue part of this graph, we can make the okay. I'm sorry that this the sharing the file is not stable. So and if we get this we get this result, we can make the PD probability distribution function as 지금 여기서 I'm sorry that sharing the displays continuously disconnect. So yeah, I'll continue this. If you the model give this left side graph, it's the result of this the proposed model, which can give each quantiles with their corresponding uncertainties. If you focusing on and getting the points from the start and the end of the time period, we can get the PDFs for PDFs which is shown in the left side, right side. And if you get these such PDFs, we can perform frequency analysis just as usual. And the trend test has shown some interesting results. Main candle test is show that statistically significant linear trends shown in only 3 out of 50 stations. KPSS test shows significantly non-stationary on the 6 out of 50 stations, and the ADF test showed 16 out of 50 stations found to be significantly non-stationary. But from our method, if we compare the PDFs from the start of the record period and end of the record period, we show 32 out of 50 stations have found to be different distributions and statistically significant. And after that, we have made some simple categorization depending on the mean change in the mean and the variance of these distributions. And we have found 6 categories from this method, and each category has their own identities. If you see the category 3, which is which is the mean is improved with the variance over the time. In consequence of that, we can get more higher design rainfall values for the same return periods. So each category has their own characteristics, and we have plotted that on the map. And if you see the map, the blue triangle is the category 3, and if you see the red box, it is category 3, and the trend is going up over the time, and variance is getting bigger over the time. So which means this which means the design rainfall value will be higher over the time period. So this is our finding, and from the result, we can conclude some conclusions. This study proposed the BM and PR model to assess non-stationarity by exploring distributional changes in the rainfall data over the period of 73 to 2015 in the South Korea. The key finding from this study can be summarized as follows. The approach would give more comprehensive information on the change than the linear regression model. We identified 7 categories from the distributional change in the from these 15 stations, and most of them was category 3, which is explained previously, and which is design rainfall value is getting bigger, higher over the time period, and then also category 7 was the second most occurred classified category, and which was the which was downward convergence, which means the design rainfall values will be getting more less. And for the category 1, 2, 3, and 6, there was noticeable the design rainfall increase observed, and in contrast, category 4, 5, and 7 showed no evidence of associated with the risk of increasing extreme rainfalls. And it should be noted that the categorization process is still adapted in the ad hoc manner according to the distribution change in the rainfall. In this regard, the future work will be focused on developing more systematic approach to explicitly combine the likelihood of function of categorization process with a hierarchical Bayesian model framework. And this is my presentation, and thank you.
Okay, thank you for the interesting presentation. And we have time for one quick question, if anyone have. If not, we move to the next presentation with speakers Suwandi Chandrasekhara and Hyun-Han Kun from Sejong University, with the title Exploring Flash Drought and its Relation to Atmospheric Circulation. Are you here and are you ready to present? Okay, so you have, maybe because we finished at 10:35, so you have around 10 minutes to present your presentation. Because we have one more presentation after this. So please start your presentation.
Circulation. I am Suwandi Chandrasekhara. Hello, ladies and gentlemen. Today I'm going to present our research on exploring flash drought and its relation to atmospheric circulation. I am Suwandi Chandrasekhara from Sejong University. The presentation consists in following order. As an introduction, flash drought is one of the newly emerging type of drought in the world due to its sudden onset, its rapid intensification of the condition. Finally, it gives severe impacts mainly for agriculture. Before going into deep, let me explain how does the drought happen. It is due to the moisture imbalance on the ground due to below normal rainfall and above normal evaporative demand due to the evaporation from the bare lands and surface water and the evapotranspiration from the vegetative surface. For the flash drought, the evaporative demand or the thirst for the atmosphere plays major role. There are two types of flash droughts. The first one is the high temperature driven flash droughts. This was observed when there is high temperature in the atmosphere, but there is no water limited condition in the soil. Therefore, evapotranspiration increases with time because of high temperature, and at the same time, evaporative demand also consecutively increases, and with time the available soil moisture is depleting. The second type is the water deficit driven flash droughts. In this case, where the water is limited in the soil surface and evapotranspiration gradually decreases, but evaporative demand is increasing gradually. So how we can calculate evaporative demand? Using reference evapotranspiration based on the temperature, humidity, and the wind speed and the solar radiation from the FAO derived Penman-Montieth equation. And further, we can measure from potential evapotranspiration and pan evaporation. The evaporative demand drought index, EDI, is a drought index which shows the anomaly in daily evaporative demand aggregated over a specific time at a given location. So what is EDI? EDI is useful in identification of onset of flash droughts and provide information for early warning. EDI can be calculated over a desired time windows, and EDI is not sensitive to land cover type. Therefore, we can use it for any region. However, EDI does not measure ground condition, though it is influenced by the available soil moisture. EDI does not predict drought, but provide an indication of drought. Finally, EDI does not measure actual evapotranspiration. The calculation of EDI, it requires a temperature, humidity, wind speed, and solar radiation, and the evapotranspiration is calculated from the Penman-Montieth equation. Then the derived evapotranspiration converted into probability of reference evapotranspiration, and then finally developed the EDI. So let me show a brief comparison of EDI and with the other drought indices, where the EDI uses the anomaly of evaporative demand derived from the temperature, relative humidity, wind speed, and the solar radiation. We can calculate EDI for a desired time duration what we require. However, the simplest, the drought index, the standardized precipitation index, only use rainfall as a data, and the other methods requires many variables, and sometimes they cannot calculate for the desired period what we required. So the problem statement in our study are that how we can use this evaporative demand drought index when there is limitation in the data, and can we apply surrogate model like Hargreaves equation to derive the reference evapotranspiration instead of Penman-Montieth method developed by FAO 56 method. Therefore, objective of the study aims to develop surrogate model using Hargreaves equation and thereafter apply derived reference evapotranspiration to estimate EDI for South Korea. So this is the methodology what we applied in our study. In the first part, it is to derive reference evapotranspiration data from the Hargreaves equation. So this is the Hargreaves equation, and it contains Hargreaves coefficient and average temperature and maximum and minimum temperature. We fed FAO56 reference evapotranspiration data to the WinBugs program and estimate median reference evapotranspiration using Bayesian approach to get maximum likelihood of the parameters. Then the estimated reference evapotranspiration was plotted against the observed reference evapotranspiration, where the uncertainty boundary is fixed to 97.5%. The second part of the methodology is to develop AD and the SPI. The log normal parameter was estimated using cumulative distribution function of the probabilities of reference evapotranspiration using the climatology of 1973 to 2010. Then eddy was estimated using the inverse normal approximation applied by Vicente Serrano in 2010. Then we developed the weekly and monthly eddy, and we developed SPI index for 3 months and 6 months and 9 and 12 months periods up to the 2000 to 2019 as a interested time period. So here is the results. In our first methodology, first I will discuss about the stations nearby the coast of South Korea when considering the developing the Hargreaves equation. The previous studies showed that the average reference evapotranspiration is higher in south and east coast of South Korea. In our study, Hargreaves equation was able to capture the high reference evapotranspiration data values in the coastal regions. However, it could not represent the lowest reference evapotranspiration values in these stations. When considering the inland stations, the Hargreaves equation was unable to capture the lowest reference evapotranspiration values as shown in the coastal regions also. But it overestimated the maximum reference evapotranspiration values. However, the flash drought identification requires only the highest values of evaporative demand, and the evaporative demand is always higher than the reference evapotranspiration. However, when considering the R-squared values in inland stations showed higher correlation compared to the coastal regions with reference evapotranspiration from the FAO56 method. Let's move on to the results derived from the AD. The station which I have selected is Gangneung. It had a severe rainfall during 2002, and in that case the weekly EDDI showed sudden drop, which shows wet anomaly in the evaporative demand. In the Namwon station, the lower rainfall periods represent positive AD, like this, positive AD, which means dry anomaly in evaporative demand. In Yangju Station, the dry period during 2011 had both short duration and long duration in the AD index to be positive. You can see they are positive and the positive during this during the 2011. Therefore, these are our conclusion. The developed surrogate model, the Hargreaves equation, was capable on estimating higher reference evapotranspiration for the stations in South Korea. However, Hargreaves equation overestimated reference evapotranspiration for inland stations in South Korea. But the coefficient of determination, the R-squared, between simulated reference evapotranspiration from Hargreaves equation and the FAO 56 for the inland stations is higher compared to the coastal regions in South Korea. Therefore, Hargreaves equation can be used for the station where there is limitation in data. The shorter period of AD captures the rapid intense extreme event like typhoon-induced extreme rainfall and the persistent dry periods. The longer timescale AD captures the slower initiation of the drought process. Therefore, AD is suitable to identify flash drought in both shorter and the longer timescales. So this is the reference which I have used, and thank you.
Okay, thank you for the presentation. And we move to the last speaker of this session. The speaker is Quang Tường Võ and Daekyo Bae from Sejong University with the title Recent Trend of Extreme Drought in South Korea. Are you ready?
Good morning, everyone. Wait a minute. I want to share the screen. That's difficult here. Can you hear me?
I can hear you, but I cannot see the presentation file.
That's difficult.
Yeah, that's good. We can see the PPT file now.
Oh, can you hear me?
Yes, you can start now.
I can't hear anything. Oh, yeah. Hello? 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 Hello?
You can start now, Tưởng.
Hello? Oh, I can hear any. Do you hear me? Good morning, Professor Tan and everyone. Today I would like to introduce a study about the recent trend of extreme drought in South Korea. The content of my presentation include 4 parts: background of study, material methods, and some results from the recent extreme drought in South Korea. And finally, we extract some conclusion. The motivation of this study, as you know, drought is a complex national disaster in worldwide, and recently drought has occurred in many countries. And you can see in China 2010, California 2012, Korea 2015, and Australia in 2018. They are experienced with extreme drought. So in my study, we would like to propose a framework to estimate the trend of drought. Our framework includes 4 parts. We use the natural drought index for estimate drought, and the second we use interpolation model to make the continuous survey of drought, and then we use the simple static Mann-Kendall test to determine the trend of drought. The Mann-Kendall combined with the zonal statistics to estimate its district for drought. In this study, we use the data from the 59 state weather stations from the ASOS. It includes the daily precipitation, maximum temperature, minimum temperature, average mean temperature, and so on. Then from this input, we use the invariable infiltration capacity model to simulation the runoff and stormwater. Then they are on the principal component analysis. We derive the natural drought index as the screen in screen. In this study, we talk about zonal statistics. What is zonal statistics? In the map algebra or raster calculators, the information can categorize into 4 classes: local, focal, global, and zonal. The local are based on information from the one bit cell to another bit cell. Otherwise, in the local, we can infer from the one bit cell inserts into the multiple pixels in the second picture, and the focal status mean that we extract information based on the neighbor of the pixel. And finally, in the local status, we will estimate for a regional of pixel. In the regional, we can estimate minimize, maximize, and also the standard deviation or percentile or extreme estimation. Here we provide you the main